Dear student, today we will discuss the chapter number 3 of Mechanics of Structure subject, that is elastic constants. The 3.1, that is the first part of this chapter number 3, is linear strain, lateral strain, Poisson's ratio, biaxial stress, triaxial stress, volumetric strain, change in volume, and bulk modulus. In this today's lecture, I will explain all these terms. Then in next lecture, we will solve problems based on this theory. Now consider a bar of length L and the cross section of the bar is say B by D or T by B, means T stands for thickness, this T stands for thickness, or D is depth, B is the width. Now we are considering the rectangular cross section bar. It is subjected to a tensile force P, axial tensile force P. Now due to this P, what will happen? The length of the bar will increase. The increase in length of bar is say total is delta L. Suppose increase in length of the bar is delta L. Simultaneously, what will happen? The cross-sectional dimension, the thickness, the width, or in case of circular bar, the diameter will get reduced. Remember, due to axial tensile force. This will happen. Now, the reduction in the cross-sectional dimension is delta T, that is reduction in thickness, or delta D, that is reduction in diameter of the bar or depth of the bar, and reduction in width of the bar is say delta B. Now the linear strain E linear is given as along the length the change in dimension divided by original dimension. So E linear is equal to change in length divided by original length. Now, according to Hooke's law, we know that modulus of elasticity E is sigma upon E, that is stress upon strain, is equal to modulus of elasticity. Then, in this case, we can write E, this is E linear, is equal to sigma upon E. Just remember this equation. It is required afterwards. Now, as I told you, due to this axial tensile force, there is reduction in cross-sectional dimension, that is lateral dimension. Then the change in lateral dimension divided by original lateral dimension is known as lateral strain, E lateral. E lateral is what? E lateral means change in cross-sectional dimension. It may be thickness. Then if you are considering thickness, change in thickness divided by original thickness. If you are considering the width, then change in width divided by original width. And if it is a circular cross section, circular bar, then change in diameter divided by original diameter. This is lateral strain. Now the Poisson's ratio is the ratio of lateral strain to linear strain. Poisson's ratio is a ratio of lateral strain to linear strain. Now it is denoted by m, 1 upon m, or mu. Poisson's ratio is denoted by mu or 1 upon m. Now here you can see that E lateral is equal to mu into E linear. So this is another equation you will remember, that is E lateral is equal to E linear. Now according to the definition of Poisson's ratio when a homogeneous material is loaded within its elastic limit. When a homogeneous material is loaded within its elastic limit, the ratio of lateral strain to linear strain is constant and is known as Poisson's ratio. It is denoted by m or mu. The value of m is 3 to 4. That means mu is equal to, which is 1 upon m, is mu is equal to 0.25 to 0.34. This value of mu is between 0.25 to 0.34. Now, let us consider a stress system, biaxial stress system. Biaxial, bi means two. Here, the body is subjected to stresses in two mutually perpendicular direction. Say x direction and y direction. So, if the forces are applied in two mutually perpendicular directions, say x and y, then they are called biaxial forces, and the body is said to be under the action of biaxial stress system. Now let us consider strain in x direction, that is Ex. Now due to sigma x, Ex is equal to sigma x upon E, that we studied earlier. Due to sigma x, strain in x direction is sigma x upon E. But due to sigma y, there will be strain in x direction, which is called as lateral strain, and to calculate lateral strain, we will have to multiply the linear strain by mu. So sigma y upon E is the linear strain in y direction. But as we require strain in x direction, that is in lateral direction, we will multiply it by mu. And remember, the lateral strain is always opposite of the linear strain. Now, for example, here as we are applying tensile force, there is increase in length, but correspondingly decrease in cross-sectional dimension. So, the tensile stress produce positive, means increase in dimension along which it is acting, but it reduces the cross-sectional dimension. So therefore it is opposite. The lateral strain is always opposite than linear strain. Therefore I am giving minus sign here. So I will repeat, due to sigma y, strain in x direction is mu sigma y upon E, but of negative sign. Here I am considering sigma y is tensile and sigma x is also tensile. So sigma y will produce positive effect on x direction but negative effect on y direction. Sigma y will produce, as it is tensile, positive effect on y direction and negative effect on x direction, opposite. Therefore, total strain in x direction is sigma x upon E minus mu sigma y upon E. Similarly, total strain in y direction due to sigma x, Ey, strain in y direction, again with respect to sigma x, it is lateral in y direction, so I must multiply it by mu, and as sigma x is tensile, it will produce reduction effect on in y direction, so minus. Sigma y is tensile, it will increase the y dimension, and therefore it is sigma y upon E. The strain in y direction is sigma y upon E. So total strain in y direction is minus mu sigma x upon E plus sigma y upon E. Okay, now this is known as biaxial stress system. You will have to remember this formula and this formula. Very simple to remember. See, strain in x direction, sigma x upon E. This is due to stress in x direction, but there is strain in x direction due to stress in y direction, that is lateral. So we will multiply to get lateral strain by mu. Mu is the Poisson's ratio, mu sigma y upon E. And as sigma y is tensile, it will produce negative effect, that is reduction in x direction. Therefore, I am giving here minus sign. Now, consider the stress system in which the stresses are acting along three mutually perpendicular axes, say x, y, and z. This is called as triaxial stress system. Now, here also, strain in x direction is equal to sigma x upon E minus mu sigma y upon E minus mu sigma z upon E. Remember, with respect to this x direction, strain due to stress in y direction is lateral, therefore multiplied by mu, and stress produces, the stress in z direction produces lateral strain in x direction, so multiply it by mu. Again, as all the stresses I am considering tensile, so the strain produced in lateral dimension is exactly negative, so minus sign. So also remember this formula. Then let us come to volumetric strain. This is given by Ex plus Ey plus Ez. And volumetric strain means what? Change in volume divided by original volume. Just like linear strain, change in length divided by original length. Lateral strain, change in lateral dimension divided by original lateral dimension. Similarly, volumetric strain means change in volume divided by original volume. Now, delta V by V, EV is volumetric strain, which is given by Ex plus Ey plus Ez. Now, what I will do, I will substitute the values of Ex, Ey, Ez, these values in this equation and simplify this. After simplifying, what I will get, EV equal to, that is volumetric strain, is equal to sigma x plus sigma y plus sigma z upon E into bracket 1 minus 2 mu. It is very simple. See, these values of strain in various directions Ex, Ey, Ez are substituted in this volumetric strain formula and simplified, and what I get, volumetric strain is equal to sigma x plus sigma y plus sigma z upon E into bracket 1 minus 2 mu. Now let us see what is modulus of let us see bulk modulus K. It is denoted by K. When a body is subjected to three mutually perpendicular like stresses of same intensity, remember it is important, same intensity. And what do we mean by like? Like means all either tensile or all either compressive. Now let us consider all tensile. So all the stresses in three direction, that is x direction, y direction and z direction, all the stresses are tensile and they are equal. So I will repeat, bulk modulus, when a body is subjected to three mutually perpendicular like stresses of same intensity, the ratio of direct stress and the corresponding volumetric strain of the body is constant and it is called as bulk modulus. So consider a block which is subjected to three mutually perpendicular stresses, sigma x, sigma y and sigma z. Both are, all the three stresses are equal and all are like stresses, means all are tensile. Then in that case the ratio of the stress to the volumetric strain is constant and that is known as bulk modulus K. Now let us find the relation between E, that is modulus of elasticity, and K. We know that EV, that is strain, volumetric strain, is equal to change in volume divided by original volume, which is equal to, from this equation, see, EV is sigma x plus sigma y plus sigma z upon E into bracket 1 minus 2 mu. But we are considering for bulk modulus all the stresses are equal, means sigma x is equal to sigma y is equal to sigma z, which is equal to sigma. Then what I will get, delta v by v, substituting the values of this sigma x, sigma y and sigma z as a sigma, I will get delta v by v, that is the volumetric strain, is 3 times sigma upon E into bracket 1 minus 2 mu. This is the relation of volumetric strain equal to 3 sigma upon E into bracket 1 minus 2 mu. Here I am considering all the stresses are of equal magnitude. But we know that bulk modulus K is sigma upon delta V by V. So what I will do, I will substitute this value of delta V by V in this equation. So sigma upon 3 sigma upon E into bracket 1 minus 2 mu. Sigma will get cancelled, and what I will get, K equal to 3 divided by K equal to E divided by 3 into bracket 1 minus 2 mu. Further simplifying it, I will get E equal to, that is modulus of elasticity, E equal to 3K into bracket 1 minus 2 mu. This is very important relation between modulus of elasticity E and bulk modulus K. On this relation, many times question is asked in MSBT theory examination of mechanics of structure. We will solve some problem in the next lecture. So I will summarize the portion covered in today's lecture. That is, first of all, there is linear strain as well as lateral strain. This is the case of uniaxial stress. The stress is acting along one direction. In this case, I am considering the tensile stress. So there is increase in length, but there is corresponding decrease in cross-sectional dimension. The, the change in cross-sectional dimension divided by original cross-sectional dimension is known as lateral strain. And for a homogeneous material, the ratio of lateral strain to linear strain is constant, which is known as Poisson's ratio. It is denoted by mu or 1 upon m, where m varies between 3 and 4, and therefore mu is equal to, that is Poisson's ratio is equal to 0.25 to 0.34. Then we consider that when we are considering E lateral, we will have to multiply E linear by mu, because mu is what? E lateral divided by E linear. Now we consider the biaxial stress system in which the stress is acting along two mutually perpendicular axes x and y. Here I consider both stresses are tensile. Then I calculated the effect of sigma x on Ex as well as on Ey. When I consider the effect of sigma x on Ey, that is strain in y direction, I multiply it by mu. When there is opposite direction, means when I consider the effect of sigma y on strain in x direction, I multiply it by mu here. So if on the left hand side you get Ex, on the right hand side if there is sigma y, you will multiply it by mu to get the lateral strain. And lateral strain is always opposite to that of linear strain, means due to the tensile force, if the length is increasing, then the cross sectional dimension decreases, and if the stress is compressive, what will happen? In that direction the dimension will reduce, but in lateral dimension, lateral direction, the dimensions will increase due to compressive force. Now then we consider the triaxial stress system in which the stresses are applied in three mutually perpendicular directions x, y and z. Then there will be strain in all the three directions Ex, Ey, Ez. Just like in case of biaxial stress system, I consider the lateral strain. To calculate the lateral strain, I multiply that sigma upon E by mu, that is the Poisson's ratio. Then volumetric strain is given by Ex plus Ey plus Ez. What is volumetric strain? Change in volume divided by original volume. Then substituting the values of Ex, Ey and Ez, I got a formula. Volumetric strain is equal to sigma x plus sigma y plus sigma z upon E into bracket 1 minus 2 mu. Then the concept of bulk modulus. When a body is subjected to three mutually perpendicular like stresses of same intensity, this is very important, like stresses and of same intensity. Like stresses means either all the three compressive or all the three tensile and of same intensity. Now here I am considering the tensile stresses sigma of equal magnitude in x, y and z direction, then the ratio of the applied stress sigma to volumetric strain is constant, which is known as bulk modulus and denoted by K. Then we derive the relation between E modulus of elasticity and the bulk modulus. So volumetric strain is delta V by V, which is equal to sigma x plus sigma y plus sigma z upon E into bracket 1 minus 2 mu. Then, as in case of bulk modulus, sigma x is equal to sigma y is equal to sigma z is equal to sigma. Then I will substitute the values of sigma x, sigma y and sigma z as only sigma. So what I will get? The volumetric strain delta V by V is equal to 3 sigma upon E into bracket 1 minus 2 mu. But K is equal to stress upon delta V by V. Here I will substitute the value of delta V by V as 3 sigma upon E into bracket 1 minus 2 mu. Sigma sigma will get cancelled, and after simplifying I will get the relation between modulus of elasticity E and the bulk modulus K as E equal to 3K into bracket 1 minus 2 mu. So this completes the theory part of the portion 3.1. Thank you. In the next lecture, we will discuss about 3.2 chapter.